Hello everyone, my name is Hoang. I am a senior at Worcester State University. I am here to present my project with Dr. Malakar. It is on using an ordinary pen as a lab tool to learn sprint constant. Introduction. The sprint constant of a sprint can be found if the force exerted on a sprint and the displacement of the sprint unknown, using the famous Hooke's law. F equal to negative k times x. F is the amount of force exerted on the sprint. K is the sprint constant. X is the displacement of the sprint when it is stretched or compressed. Sprint or elastic potential energy is the stored energy of a sprint or sprint-like object when it is not in an equilibrium position, that is, when it is stretched or compressed. It is known as 1/2 k times x squared. K is the sprint constant. It measures a sprint stiffness. The larger the K value is, the stiffer the sprint is. It has a unit of Newton per meter. Another important concept is the gravitational potential energy. It is the stored energy of an object when it is placed at a certain height. It is known as U equals to mgh, that is the mass of the object times the value of gravity times the height the object is at. In figure 1 is shown the two forms of potential energy. On the left is showing the elastic potential energy. A bungee is being stretched and is ready to return to its equilibrium position and releasing that stored energy once it's stretched into kinetic energy and launching the man upwards. On the right is showing gravitational potential energy as example by a woman about to dive off a cliffboard. As she step off the cliffboard or dive off the cliffboard, see it as a certain height. And she is ready to convert that stored energy into kinetic energy and enter the water surface. In this experiment, a pen sprint was compressed at varying compression length and released to launch a pen cap upward. It looks like this. The initial and final position of the pen cap were recorded to determine age. The initial position of the pen cap is when the sprint is already compressed. The final position of the pen cap is when it is at the maximum height after it was launched. The difference between these positions give us age. To do further calculation, we have to know the mass of the pen cap. Due to COVID-19 and the lack of access to our facilities, we have to use the post-office scale to determine the mass of the pen cap. Using the conservation of energy equation, we have the work plus the kinetic and potential energies of the sprint is equal to the kinetics and potential energies of the pen cap minus any energy that is lost in the process. The work that put into the system is zero as we determine the initial position of the pen cap is when the sprint is already compressed. The kinetic energy of the sprint is zero. The elastic potential energy of the sprint is 1/2 k times x squared, as we mentioned earlier. This is equal to the kinetic energy of the pen cap to be zero as the pen cap is already at a maximum height. The velocity of the pen cap during that when it is at the maximum height is zero. Therefore, the kinetic energy of the pen cap is zero at that position. Plus the potential energy of the pen cap. At this position, it is at a certain height. Therefore, it contains a gravitational potential energy, mgh. The energy that is lost in the process we assume to be zero. Rearranging the equation for h, we derive an equation of k times x squared over 2mg. From the equation, we can plot h against x squared to obtain a slope of k over 2mg. Plugging in and rearranging the equation to solve for k, it was found to be 160 Newton per meter for the specific sprint. In figure 2, it shows how exactly we did the experiment. At each compression length, we measured the height the pen cap was launched 5 different times. The error bars at each of the compression lengths represent the standard errors. Sources for errors in this experiment includes the inaccurate mass of the pen cap. As mentioned, we measured the mass of the pen cap using the post-office scale that we don't know how accurate it is. The second source of error could be the angle at launch was not equal to 90 degrees above the x-axis. A few degree difference could send the pen cap sideways. As a conclusion, physics can be applied outside of a classroom. Our goal is to use everyday objects to get the insights of physical concepts. We want to find and use easy and accessible ways to understand physics. This experiment is relevant because many objects rely on the force exerted from the spring. Think of the human spinal column. It acts as a spring that absorbs shocks, help us balance, and help us with our range of motion as it stretches and compresses throughout the day. In the future, we could determine the force the spring could produce, the acceleration of that force, the velocity of the object as it leaves the spring, and how high the object will be after its launch. We hope that this experiment is useful for teaching and learning exercise to understand the basic physics principles. I'll be happy to take any questions. Thank you so much for listening.